have this tiny kiln that is perfect for me, and I bought it off a classified ad a couple of years ago from a starving archaeologist, as it turns out. She swore she was cutting me a deal since I was using it to knap and not loot arrowheads. So there you go, guys. Hopefully she's less hungry after I bought it. But the kiln used to be relatively cheap a few years ago. It was about 450 bucks. But I looked and it's now about twice that price. So it is what it is. At any rate, I do love it, but it has this really annoying issue. It doesn't have temperature control at all, and instead it just runs on a mechanical timer. And even if I put it on its lowest temperature settings, it can easily reach 500 plus degrees and requires tons of manual babysitting. It's just impossible to manage for a long run. A couple years ago, I made a test attempt to digitize it, and was pretty encouraged by that effort. So today I'm going all in on it, and I'm making the code I've written for it all available on GitHub for anybody else who wants to try it. This is an Arduino Uno. I actually have a program, and I don't need this big Uno, and won't in the end. But it's nice and easy for testing. I had my existing thermocouple reader, but I got a new thermocouple, some big long ones. I'll install those in the kiln. So anyway, I just breadboarded everything up and was testing it. Also, I changed how I'm doing all my power and everything. Just got a box. The hot wire is clipped between the two segments. So this one always has power, and this will power the Arduino, is the idea. And then this one will power the kiln. The Arduino temperature reads, makes its decisions about whether it needs to turn the kiln on or not, triggers the solid state relay, which has the hot, and allows the heater to turn on. This is an Arduino Mini, and they're very cheap. You can even get them for $5 or $6 if you buy them in bulk. It just takes a bit of soldering to make the pins accessible. There's hundreds and thousands of tutorials on wiring, using, and programming Arduino, so I'm not going to go into any of that. But it really isn't that hard if you're even moderately technically inclined. And the program I've released is easily adjusted to your needs, so you can cook at whatever temperature or duration you want. Oh, and there's no reason this won't work for automating a turkey roaster either, since we're just controlling the power on-off. There are many types of solid-state relays out there, but this is a kind that's known as a zero-crossing relay. It has to do with the electrical wave timing of the load. There's some technical reasons these are the best type to use with heat coils, and a hat tip to Jimmy for pointing me in this direction. This relay also has a heat sink on the back. My kiln can pull up to 13 amps, which could warm up the relay. I don't think it will, but this is one of the reasons I also use the metal electrical box and attach directly to it. And quiet down out there, you electricians. I'm a knucklehead when it comes to electricity, so don't take any of my advice on how to do any of the high-powered parts of this project. Do all of that at your own risk. Alright, after a bit of assembly, let's load this baby up. I've got a few samples of some agates, some jasper, a chunk of chert from my last video, and I figured I'd try some tiger or oil chert while I was at it too. And while we wait for those to cook up, a quick explanation of some of the code parameters you can adjust to your needs. These are just the pins you can connect the thermocouple into by default. You can obviously choose others if you want. And this is the control pin for the solid state relay. By default, it's on pin 8. The start period isn't really necessary to adjust. You can just safely ignore it and leave it alone. Start temp is the warm-up temperature. The kiln or roaster will warm up to this temperature before it begins its cycle. U-ramp temp is the number of degrees per period it will warm up. So if you leave the default period of 1 hour, it will warm up by this number of degrees per hour till it reaches the hold temp, which is the next parameter. Hold temp really is the max temperature that you want to reach. I sometimes call it the soaking temperature. Hold period is the number of periods you want the kiln to hold the soaking temperature. The D-ramp temp is how slowly you want the kiln to cool down per period. So again, if the default period is left at 1 hour, it will only allow the kiln to cool by this number of degrees per hour. The last thing is the P count. This is where you can adjust the period length if you want to mess with that. But like I said, it's really set to the default of 1 hour, and that's usually pretty good. Very pleased with how this local chert came out. This rough piece of test agate also came out extremely nice. These yellow agates crazed in the process. There's obviously more work to do here, maybe less temperature or slowing the down ramp. Maybe they just don't need to soak as long. More to do. And the Milky Utah agates came out perfectly. Very glassy and very smooth. This pigeon blood agate had an interesting development. I noticed it developed these dark green spots. The area I collected these from is thought to be where the fan cache agates were sourced. Archaeologists think that because many of them have these green and yellow inclusions. This area is the only place regionally they're known to come from. There's been some discussion about whether some of the fen cache points were heat treated or not, because they're very glassy. These green spots developing when heat treated may potentially be a clue on that front. I'll be watching for more of them to appear in the future, of course. These pigeon blood agates need more heat or soak time. Still rough. I couldn't be happier with how this butterscotch jasper turned out. This is a very hard, quartzy material without heat. And finally, the tiger or oil chert. This is also another fen cache material, by the way. And yes, you can smell the oil in it even stronger after it's been cooked. This was just an experiment since I've never treated oil chert with heat at all. Overshots can be useful when the far side is pretty square, but here it's just a very nice thinning flake for me. The far side actually had a nice angle I could have used. Not sweating it though, it's a very nice thinning flake at this stage. I'll take it. Look, see? There's a flaw in the rock. It's not my fault.
Alright, well, seems workable.
Okay. The link to the code on GitHub is in the description if you're interested. Sometime I'll get a cheap turkey roaster and do some experiments with it too. It'd be interesting to see if there's a difference between the sand, using sand as a thermal mass, or maybe without it. If one of you out there decides to try it, I'd be interested in your results.